In section 3.6, we're going to learn how to take derivatives of inverse functions. Theorem 3.16 talks about the continuity and differentiability of inverse functions. Let's suppose that f is a function whose domain is an interval I. If f has an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse will be continuous on its domain. And criteria number 2 will tell us precisely when f inverse will be differentiable. Let's suppose that f is differentiable on an interval containing the point x equals to c, and so f has to be differentiable at the point, and furthermore we require that f prime of c not be equal to 0. If that's the case, then the inverse function will also be differentiable at the point f of c. Okay. So recall that the function f is differentiable at c. So on the graph of f, you would see the point c, comma f of c. So that would be a point that belongs to the graph of f. Remember, whenever you find inverse functions, if you recall doing this by hand in college algebra, that typically what you would do is you would interchange the x and the y variables, and the points get flip-flopped. So this would be like f of c, comma c, and the corresponding quote-unquote x value that would be in the domain of f inverse would be f of c. And so that's why we say that f inverse would be differentiable at f of c. So Theorem 3.16 tells us a little bit about when the inverse function is continuous, and in addition when the derivative exists. Theorem 3.17 will actually give us a formula for the derivative of the inverse function. Let's let f be a function that is differentiable on an interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0. So we have f, and in the textbook they use the notation g for f inverse, and we would get the following formula. The derivative of the inverse function, that is the derivative of g of x, is equal to 1 divided by f prime composed with g of x. Okay. In my opinion, I'm not really pleased with kind of how they write it like this. It's perfectly fine, but it kind of hides a little bit in the notation because otherwise it might look complicated to some. But I think it's kind of much better to write it with the inverse notation. So after all, what we're trying to do here is we're trying to take the derivative of the inverse. So we're looking for f inverse prime of x. This is equal to, according to that formula, it's 1 divided by the derivative of the function f, so that's f prime, and then that function is evaluated at the inverse function f of x. So f inverse of x. And you can kind of see that requirement we mentioned above on why we would need that to be 0. That's essentially going to be the denominator in this expression, and if that denominator is 0, then this expression would be undefined and we wouldn't get a value. If you're curious, so again, I'm not a big fan of just throwing formulas at individuals. It's important to be able to, of course, mechanically work with it and understand how it works. But let me just briefly kind of derive for you where this formula comes from. Okay. So let's suppose that we have a function. Let me get some white space here. Let's suppose we have a function y equals 2 to f of x. Okay. And let's suppose that we would want to find its inverse function. Okay. To involve the inverse function, I could take f inverse of both sides. So let's take f inverse of both sides. And here's what we would get on the right-hand side. Because of the nature of a function its inverse, these would compose and simply give us x. And from here, let's try to take the derivative of both sides. I'm going to take d dx of the left-hand side. And we're going to take d dx of the right-hand side. Okay. On the left-hand side, this is going to be a chain rule problem. What we would get would be f inverse prime. So if we know that derivative exists, then we're going to get f inverse prime of of y. And then from the chain rule, we would need to multiply by the derivative of the inside function. Let's call that y prime. And on the right-hand side, this would simply be equal to 1. Derivative with respect to x is just 1. We can solve this for the inverse function. F inverse prime of y would be equal to 1 divided by y prime and now if we think about it, we know what y prime was equal to. So if I come up here, y prime, that would be just our standard f prime of x. So it's going to be 1 over f prime of x. But now I want to have a function of x. So everywhere I see a y is equal to f of x. So we have f inverse prime of the following. Actually, no, we won't do it like that. Let's get rid of the x first. So if I replace the x, what is x equal to? X is equal to f inverse of y. So we have f inverse prime of y would be equal to 1 divided by f prime evaluated at f inverse of x. And there we have it. So actually, I'm sorry, this would be f inverse of y. And essentially that gives us the formula. Okay. We know that y, if you go back, if you had a point on the graph of f, that'd be the form fx comma y, which would belong to f. On the graph of f inverse, we would have the point y comma x, where y would be like a value in the domain of f inverse. Usually we don't call those y values, we call those x values. So you would kind of relabel this. It'd be f inverse prime of x, where x belongs to the domain of f inverse, 1 divided by f prime of f inverse of x. So I don't always do a lot of the derivations. Some of them are not necessarily insightful. I mean, they're all insightful, but to kind of get aside from what we're trying to focus on in the class. But the thing that I want to kind of show to you is, where did this derivative rule come from? How did we find the derivative of an inverse function? And well, the idea is we were actually able to find it by using our concept of implicit differentiation. And it just kind of goes to highlight exactly how powerful that idea is. With the concept of implicit differentiation, we're going to be able to do a lot of really interesting and cool problems. Okay, so let's go ahead and go back. Let's take a look at example 1. Let's suppose that f of x is equal to 1/4 x cubed plus x minus 1. The first thing they want us to do is to find the value of f inverse of x when x equals to 3. Let's see if we can do that. So f inverse of 3, let's see what this is equal to. So this is what we're trying to find. I don't know what it is. Let me just call it c for the moment. So let me just call it c. F inverse of 3, if you take f, apply the function f to both sides, it's essentially asking this question. What value c would I have to plug into the function f such that I get the output of 3? Okay. So what we're going to do here is we're going to take this function, 1/4, I'll call it c cubed right now, plus c minus 1 is equal to 3. And we want to solve this equation for c. I can get one side to 0, so I'm going to subtract 3 from both sides. This is a polynomial equation. We get 1/4 c cubed plus c minus 4 equals to 0. If you were doing this by hand, you would probably want to clear the fractional coefficient, multiply everything by 4. We would get c cubed plus 4c minus 16 equals to 0. And now we're to this part here. And this isn't necessarily trivial to solve this. This is a polynomial of degree 3 or higher. And what we could do is we could appeal to things like the rational roots theorem. So if you wanted to really thoroughly kind of go through this, you would be able to find a solution to this by hand. In particular, you'd want to use the rational roots theorem, which would tell us that the possible rational roots of this polynomial would be one of these: plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, or plus or minus 16. They're the factors of the constant term divided by the factors of the leading term. And if you go through the possibilities, what you would find is that the solution is going to be c equals to 2. And I can just quickly check that. 2 cubed plus 4 times 2 minus 16, does that equal to 0? Well, that's 8 plus 8 minus 16, and sure enough, that does equal to 0. As an alternative approach, one of the things that we could all do, and I would suggest that probably for this example here, is you could graph this function in a calculator, call it y equals, and then if you want to know where that thing is equal to 0, that'd be just a matter of finding the x-intercept. So for a lot of us, especially one like this, I think to find that solution would be best to perhaps use technology. Okay, graph it and just see where it crosses the x-axis. The ones that will be in the homework and the ones that I would put on any potential exam wouldn't quite be like this, where you actually have to do something exotic. They should be ones that fairly easily, using algebra, you should be able to solve for that value of c. But what we just found is that f inverse of x, so we saw this, so we saw that 3 is equal to f of 2, and therefore we can say that f inverse of 3 equals to 2. They now want us to find the value of the inverse function's derivative when x equals to 3. So let's go ahead and write out the formula for this. F inverse prime of x is equal to 1 divided by f prime evaluated at f inverse of x. And we're looking for f inverse prime of 3. This is going to be 1 over f prime of f inverse of 3. Well, we just saw a moment ago, this part was equal to 2. So it's going to be 1 over f prime of 2. Let's come back. We need to take the derivative of the original function. We can do that pretty easily. F prime of x, that's going to be equal to 3/4 x squared plus 1. And we need to evaluate that at 2. F prime of 2 is going to be equal to 3/4 squared plus 1, which is going to be equal to 3/4 times 4 plus 1. 3/4 times 4 is 3, and then 3 plus 1 will give us 4. So there we have it. The inverse function evaluated at 3 would have a derivative equal to 4. Let's take a look at example 2. In example 2, they say let f of x equal x squared for x is greater than or equal to 0, and then its inverse function is going to be the square root of x, which has domain x greater than or equal to 0. We're asked to show that the slopes of the graph of f and f inverse are reciprocals of each other at the following points. So for example, if we start with the point 2, 4, this is a point that would belong to the graph of f. You can check it, but 2 squared equals to 4. So this point belongs to f. This point would belong to f inverse. Here we can explicitly compute the derivative of f. The derivative of x squared is simply going to be 2x. And so if we evaluate that derivative at a point in its domain, that's evaluated at 2, we get 2 times 2, which is equal to 4. F inverse was equal to the square root of x. We have an explicit form for f inverse, so we can just simply go ahead and do the derivative here. F inverse prime of x, this is x to the 1/2. Power rule, we bring the power down. We're going to reduce the power by 1, and then we can reciprocate. This should be 1 divided by 2, x to the positive 1/2, but I'll just call it 1 over 2 square roots of x. So f inverse prime of x is equal to 1 divided by 2 square roots of x, and its derivative evaluated at the point in its domain would be 4. This is going to be 1 divided by 2 square roots of 4, which is 1 divided by 2 times 2, which is going to be 1/4. So if we compare these two as they said, those slopes end up being reciprocals of each other. At 2, 4, f has a slope of 4, and at 4, 2, the inverse function would have a slope of 1/4. Let's take a look with another pair of points. If we try to do f prime of 3, remember f prime is 2x, so this is going to be 2 times 3, which is 6. That'd be the point for f. The corresponding point for f inverse prime of 9. This is going to be 1 divided by 2 square roots of 9, which is 1 divided by 2 times 3, which is equal to 1/6. So the derivative of the inverse evaluated at 9 is equal to 6. And again, we see the relationship is that those slopes are going to be reciprocals of each other. In example 3, we're asked to find the inverse of the tangent function. Let's go ahead and do that. So let's start with the function y equals to tangent inverse of x. One of the things that we know is that if we wanted the derivative of this inverse function, we could simply just kind of appeal to the formula, but let's kind of work through this by using the implicit differentiation. So I start with this, I'd say, okay, I don't know right now a formula for the tangent inverse, but I do know a formula for the derivative of the tangent. So let's begin by taking the tangent of both sides. So the tangent of y is equal to the tangent of the tangent inverse of x. Because of their inverse nature, I know that the tangent of the tangent inverse, that's simply going to produce x. And now from here, what we can do is let's go ahead and take the derivative, because we know from previous stuff, we do know the derivative of the tangent function. The derivative of tangent is secant squared, leave the inside function alone, y, and now from the chain rule, we need to multiply by the derivative of the inside function. That's our implicit differentiation. That's going to be dy dx. Or you can call it y prime. Doesn't matter. I'm feeling dy dx this morning, so let's do dy dx. This will be equal to, the derivative of the right hand side is going to be equal to 1. And now we can go ahead and get dy dx by itself. So I'm going to go ahead and divide by secant squared y on both sides. Divide by secant squared y. This cancels, and now we have dy dx is equal to 1 divided by secant squared y. So far, so good. Now, recall we started with a explicit function. We had y equals tangent inverse of x. So we would also like for the derivative to be an explicit function of x. Right now it's implicitly defined. We have 1 divided by the secant squared of y, but we know what the y variable is equal to. Everywhere we see a y, we can replace it with tangent inverse of x. So this is 1 divided by secant squared of the tangent inverse of x. So that's a formula for the derivative of the tangent, but we can even do better than this. Okay. Where we have tangent inverse, so recall, what does an inverse trig function give us? Well, an inverse trig function gives us an angle. Okay, let's just call that angle theta. This relationship means, if I take the tangent of both sides, that the tangent of theta equals to x, which is the same thing as x over 1. So we can draw a sketch of a right triangle. Remember, the tangent is the ratio of the opposite over the adjacent. So if I call one of the acute angles theta, the opposite side will be x, the adjacent side will be 1, and I'm going to skip the work on this, but I'll let you show it on your own. Pythagorean theorem would tell us that this would be 1 plus x squared. So if you solve for the hypotenuse using good old school a squared plus b squared equals to c squared, we would get that the hypotenuse is the square root of 1 plus x squared, and that will now allow us to find the value for the secant squared of theta. So remember, the secant squared of theta, secant is reciprocal cosine. Cosine is adjacent over hypotenuse, so this one's going to be hypotenuse over adjacent. The square root of 1 plus x squared divided by 1 is square root of 1 plus x squared, and then the squaring term will get rid of that square root, so we get 1 plus x squared is the value of the secant squared of theta. So all together, there we have it. So this will just simply go into that denominator, and we're going to get 1 divided by 1 plus x squared. So the derivative with respect to x of the tangent inverse of x, it's equal to 1 divided by 1 plus x squared.